Good morning. Welcome to particle simulation method for fluid dynamics. So today we will have the last lecture. We will talk about smooth particle hydrodynamics, which is a macroscopic method for simulation of fluid dynamics. The smooth particle hydrodynamics or SPH method is a macroscopic method. The way SPH works is very similar like the molecular dynamic method. So that means they all solve a problem given a set of n interacting particles. And the solution is based on solving the equation of motion for each particles. But the difference is the resultant SPH method is solving a Navier-Stokes equation, and the molecular dynamics is more like solving the dynamics of the molecules. So as they both are particles, use particles on particle method. Why SPH use particle? They are solving an S equation, but the molecular dynamics use particle, but they are solving a macroscopic dynamics. The difference is for SPH method, there is one bridge which is built between the particles and the Navier-Stokes equations. This is the so-called particle approximation based on a kernel function. However, as the two methods are very similar on the algorithm because they are both typical particle algorithms. So that means there's a very strong relation between SPH method and molecular dynamics. And we can show there's if you use a very special potential function, which is obtained from the kernel approximation, you can find SPH method can be look like a special form of molecular dynamics with special potential functions. So this simulation between the two make this SPH method very similar like molecular dynamics. That means sometimes they may have a trouble of so-called artifact of macroscopic artifacts, because SPH method they are solving macroscopic problem, but sometimes their behavior is like a microscopic approach. So, but this microscopic approach is not a physical, because physically SPH method need to solve macroscopic physics, should be only represent macroscopic behavior. Okay, we look at the basic concepts of SPH method. So the basic of SPH method, basically it began from how we can use particle to do approximation. So to know how particle do the approximation, we first would like to begin from the mesh-based method or traditional CFD method, how they use the way to approximate to achieve approximations. For example, if you have a typical mesh method, like find a difference of a volume, and you have value, for example, if we consider find a volume method, you have a cells, computational cells, and each cell have one cell center. And if you want to achieve approximation, for example, if you have a cell center value, if you want to approximate the value at this corner, so-called cell corner, then you basically you use the 4 neighboring cell center value to approximate by writing approximation like this. So the approximate corner value would be with the average of the 4 cell center value around this cell corner. So basically you can write a form like this, average of the 4 values. And if you split each value with 1/4, then you can write in a form like this. So basically is a summation for all neighboring points. Then you can write a summation form like this. So the approximation of the corner value would be equal to the summated average of the 4 neighboring cell center values. Then you can write in this form. And this summation form will give you each value, or we can call it a candidate value for approximation, and each value got their weight. And we can see clearly all the weights add together would equal to 1. So this will lead to so-called consistency condition. That means if all the 4 values will be same, and this approximation will lead to the same value. So basically, if we do approximation in a mesh method, this is basically the way we are using for approximation. So how can approximate if we don't have a mesh and we only have a disordered particles? But actually, we do a very similar case way as we did before. First, we choose neighboring particles for approximation. For example, if we want to approximate some value at this position, and then we only look around this position and we find some candidates, and this look around we call it a neighborhood, which we can find a cutoff radius, something like we use for molecular dynamics. Then within this cutoff radius, we will find the neighbor particles which we can use for approximation. And we do the same as we did before. We write the approximation as a so-called average, a weighted average, or summation with weights. And we also require all the weights add together equal to 1. Then we can also do approximation with disordered particles. So now the situation is how we can find the weights. In the previous case, all the candidate points for approximation has same distance to the cell corner value. So they have the same weights. And here, as the points or particles are disordered, we don't have each same distance to the point we would like to have approximation. So we would like to choose the weight of the approximation depends how far this particle around away from this point which we would like to have approximation. So naturally we can say if the particle is close to the point, then we will use larger weight. And if the particle is further from this point, we will use less weight. So basically we will use the weight depends on the distance. So that's the way we can do particle approximation. How exactly to choose the weight? We need to introduce a kernel function. So with this requirement of approximation, that means all the weight add together equal to 1, and the weight will be less when the particle is far from the approximation point. So with this condition, we can choose one function which have a decay property like this. So if we choose a function WR, and if we relate with distance, and if distance is small, then have big value. If distance large, then have a smaller value. With this form, we can define a kernel function have this weight. And we also hope all this weight add together. That means if we find the kernel function's integral in the entire space equal to 1, then will help us to achieve this so-called consistency condition. And the integral equal to 1, we can basically write in this form to approximate the integral by a summation of weights, the function value, and times the volume of integration. So in this case, then we can write this element of integration equal to the weight which we are using. Then we can write the final form like this way. So basically, the approximation of I equal to the each particle around and related with particle's volume and a function value of the kernel value, and the kernel would have a property is integration of this kernel would equal to 1. Then we can satisfy these two conditions which we required for approximation. So with a little bit formal validation, we can find the kernel function we are using for approximation would have some special properties. For example, they should have a so-called reduced symmetry property. As we say, the weight of approximation is only relevant to the distance. So that means this function will only relate with distance, is not related with direction or anything. So that make this function should be reduced symmetry. And then second, they should have so-called compact property. This is same as the cutoff radius, because we hope this kernel function only have a value within the cutoff radius, so we don't need to consider many particles around for this approximation. So this two property, another property is the function's integral should be equal to 1 in the entire space. So that property make this kernel function is actually approximation of this Dirac delta function. Because we know the Dirac delta function has a property if his integral around the entire space would be 1, and yeah, but the Dirac delta function has is more like is a function with actually is a very high peak pulse. So this is delta function. So we don't want to have this so high peak. Then basically we just smooth this delta function. We use the smoothed form to use it for kernel function. And then you can find the kernel function is more like a smooth version of the Dirac delta function. And as we know, Dirac delta function has a very special property. This the special property is the function. If this one is Dirac delta function, the integral of this delta function together with any function will be the ended value at that point, at the central point of the Dirac function. So that's the Dirac delta function's property, and the kernel function would have a similar property like this, because this kernel function is basically a smoothed version of a Dirac delta function. That means this term is not exactly satisfied, but approximate satisfied. So if we choose a Dirac delta function to do approximation, so then basically you can discretize the approximation with the kernel function by this way. So now we need to have so we can calculate each kernel function's value, but we still need the volume element. So how can we obtain a volume element? As we do fluid dynamic simulation, the volume can be calculated from a mass divide the density of one particle. So if we know the particle's mass and we know the particle's density, then we know the particle size. Then if we know the size, we can know the element, integral element there. Then we can do this approximation. So then we can write the final approximation form by this way. So to approximate the value at A, we need to have many particles around. Each particle have a mass and density, and we can calculate kernel value according to distance, and we have this values on those particles. Then we are able to obtain the approximation. So with this special form we have already chosen for approximation, then the first thing is how can we approximate density, because density is one of the basic variables for CFD. So if you want to approximate density, then here will be a density here, and this would be also a density. So then you just insert this into density and you can approximate density. But if you insert the density, particle density here, and you can find, because for the volume element we also have a density there, so both density will cancel each other. Then we enter the density approximation in SPH. It's basically equal to the summation of all kernel value times the particle's mass. Then is the density of the flow. And we can also, to validate that the consistency condition for SPH method. That means if we want to approximate a constant value, theoretically, the approximate constant value should be same as this constant value. That means if all the particles have value 1, the approximation should be ended with 1. That means if you insert this 1 inside, you need equal to 1. That means this value should be equal to 1. That basically means the integration of this kernel function is equal to 1. But the situation is we are not exactly calculating this integral. What we do is by discretized summation. So this is only approximation of this integration, and basically that means in SPH, if we approximate one constant value, we only achieve approximate approximation. That means if we approximate 1, every particle have value 1, but the approximate value would be not exactly equal to 1. That is a special property of SPH method. That means you don't have exact reproducing constant a constant field. So with approximation of value, and we can also derive the approximation of gradients in SPH. Basically, this can be done by introduce a integral by parts, because as we saw before, we have the integration of one value, and this one we approximate value at R. That's not good. So value is R prime equal to this integral. That's based on the property of the kernel function, and as by integral by parts, we can say if we want approximate the gradient of some value, so we basically can do the same. And as this one, we can introduce basically integral by parts. This first part is this one. minus the second part and we know because the kernel function has a compact support, that means we lead this will equal to 0, then the approximation of integral would be only the second part. The second part, then we approximate. The second part would be approximate equal to summation of all particles, j particles, and the gradient value and Vj. And Vj actually is mj divided rho j. So that's the approximation of gradient, which you can obtain from SPH method by particle approximations. And theoretically, if you have approximate the gradient of a constant value, then basically they lead to 0 because the gradient of a constant value is 0. Even so these two add together or minus each other will not change anything. So basically we can rewrite the approximation of the gradient in a form which we introduce the two points, the value at 2 points minus each other. So basically we can obtain approximation of a gradient at one point by this approximation. Certainly the divergence of one vector, if we just simply change this gradient to dot product, then we obtain the approximation of divergence. So that's the approximation, particle approximation of gradient and divergence in SPH. So with a little bit more involving some simple mathematical operations, we can still approximate something like a density times a gradient or density times a divergence. So basically, if you use this this relation with combined derivatives, then together with the original approximation, we can obtain the density times one gradient into a form like this, or density times one dot divergence with this form. So we will use this one to discretize the Navier-Stokes equation. So in order to discretize Navier-Stokes equation, we still also need to approximate something like a divergence divide density or divergent gradient divide density. This because we know the momentum conservation equation for in a Lagrangian formulation would be equal to gradient of P divide density plus the viscous terms. So basically we need to approximate this term. So this term, and if B is more like if we do solid, then this one would be the stress. So we also need to do this term. So basically, with similar with density times gradient or divergence, we can do approximate some mathematical operations, and we obtain the final formulation for basically this one is for pressure to approximate pressure gradient. This one over the force divergence of the stress tensor. So with SPH, then we can discretize the momentum equation. Actually, we also need other things. For example, for Navier-Stokes equation, we need also approximate the Laplacian. The Laplacian of one variables here is more like this the tensor form of the Laplacian because there's a Laplacian vectors. So basically, we can also introduce here. We don't show how we derive this, but we can also use SPH to approximate the nabla this tensor by this form, where here is a d is dimension and the eij is this vector between two particles. So if one particle is I and particle is j, then you have Rij equal to Ri minus Rj, so vectors. So Eij is basically means the unit vector of this. So with this, then you're able to approximate the Laplacian by particle approximation. So now you have basically everything operators approximated. Then you can apply this operator to discretize the Navier-Stokes equation. Before we do the discretization, we need to choose the exact form of this kernel function. In real case, we very often people choose a kernel function uses piecewise continuous, especially some kind of a Gaussian-like function. So this one is a typical one called the B-spline function. So this B-spline function was used to approximate the kernel function, and in order this B-spline function, you can see this function would be only have a value, non-zero value when the R between 0 and 2. So that means we have a cutoff of 2. And here we define a cutoff relate with this so-called smoothing length. So this one would be smoothing length. And the cutoff, in this case, cutoff reduce will be equal to 2 times h. So because when you normalize the distance with the smoothing length, then with smoothing, when the distance normalized is larger than 2, the value will go 0. That means cutoff radius is 2 times of h. And in order to make this this is only 1D formulation. In order to achieve integration of entire space equal to 1, then we should introduce a 1 factor in front of this kernel function. So for different dimensions, for second 2 dimensions, 3 dimensions, 1 dimension, they have a slightly different value. Not slightly different value, but they are different factors because we need to normalize the integral. Now we can use discretized operators to approximate the Navier-Stokes equation. The first one, we approximate the density equation. So as we showed before, in SPH, we can approximate density by this summation. And is still another way if we write the density formula evolution equation in Lagrangian coordinate. If we can discretize a rho times divergence of velocity, we can also discretize the evolution of density. Then you can have another approach to approximate the density variation by introduce approximations from the right hand side of this divergence and density. Then you have a second approach to approximate the density. And basically this two approach both have some benefit and shortcoming. One of the shortcoming of the first equation is when you have considered some special situation one of the situations is you have a so-called free surface flow. For example, we have a container, and we may have some flow inside the container. In this case, if we use the summation approach like this approach, we need to define a cutoff radius. But if you have a fluid near the surface, free surface, because here you have a fluid. No, I don't use this one. Use another color. If you have a fluid, then you do a summation, then you can find the outside region is void because we don't have a free surface. That means only have liquid. You don't have you don't have air. Just consider liquid and empty place. Then you have empty place. Then this region you have no mass. Then basically this way you approximate wrong density. So in this case, we need to use the second formulation, this evolution approach, because this approach don't need to mind if you have a void region or not. So we can have an evolution equation to approximate the density variation. So very often we are basically approximate incompressible flow with SPH. So SPH usually don't really do the same as people do traditional CFD. When they approximate incompressible flow, they solve a Poisson equation related with density field. And in SPH, we basically use a so-called weakly compressible approach. That means we assume the flow is weakly compressible. That means the density variation is not big. By introduce a somehow stiff equation of state, then we can control the density variation inside the flow is around 1% or around that value. So in this case, the density of a fluid will not change much. Then the flow which we obtained is a weakly compressible flow. The physics is very similar like incompressible flow. And we use this simple approach to approximate incompressibility. We can also discretize the equation of motion. So the equation of motion, if you write the equation of motion of fluid in a Lagrangian coordinate, the velocity or the acceleration of each particles were modified by gravity, the pressure gradient, and the viscous force. And as we already shown, we have the approximation of this term, approximation of Laplacian. Then we can basically discretize Navier-Stokes equation in a simple way. So here we give the discretization for the pressure terms. So the pressure induced acceleration will be given by the right hand side. So basically you have two particles pressure, and you will have this right hand side, and you can see with this formulation we satisfy the momentum conservation, because if you switch I and J, you can obtain opposite force, because this will not change, but the kernel gradient, if you switch Ji, the sign will change. So basically it means for each one pair of particles, we have a force and a reverse force equal to each other with opposite sign. And from this formulation, we can still find that SPH can relate to molecular dynamics in a very special way. For example, if we define an equation of state related with the density square, so if pressure is related with this, then we can insert the equation of state into this equation, into the discretization. Then you can find if still also assume all the particles have same mass, then you can find we can derive the SPH formulation like this. If we insert, then the density will cancel each other, only one C left. Then you have a C with kernel, and then you can see the kernel is some special or potential function, and this force can be a potential force. So in this case, SPH can be explained as a special form of molecular dynamics if we don't consider viscous force. But the SPH we will consider viscous force, so it will be slightly different. By the Laplacian approximation, we can basically obtain the discretization of viscous force. And this viscous force can be introduced with the difference between the two particles density. Here it basically means Vij means Vi minus Vj. Related basically on their related velocity. And this formulation is also satisfying the conservation of momentum. So basically, SPH method have very similar property as molecular dynamics because they have a mass conservation because every particle's mass basically don't change as we use Lagrangian formulation, and then momentum is conserved because all the formulation is right in the form and of force and the reverse force. So basically, that's the SPH method. They have very good conservation property, same as molecular dynamics. Here is implementation of SPH and his flow chart. And if you look at the flow chart, you can find SPH is very similar like molecular dynamics and direct simulation Monte Carlo. Basically, you can see the step is after initialization, we'll transport this molecules. This here is not molecule, it's particles, and we do cell link list for the search. And when after impose boundary condition, here we don't give the details, and we will calculate force, same as molecular dynamics. After calculate force, we move the particles again, and this loop is very similar like molecular dynamics. And the difference between SPH and molecular dynamics is because we are a macroscopic approach, we don't need to do average to obtain the macroscopic state like pressure or density because those are the independent variable within the algorithm. So the computational efficiency basically is the same as molecular dynamics because we need to build up the cell link list and if we need to search the neighbors. So this efficiency is the same. But compared to direct simulation Monte Carlo, the efficiency is lower because, as we know, direct simulation Monte Carlo, they don't need to search the neighbors. They just consider those pairs within one cell. Yeah. And another thing, as we mentioned before, as SPH can be write in a special form of molecular dynamics with a special term or form of a potential force for the pressure pressure force in the Navier-Stokes equation. So basically, that means SPH share very similar property as molecular dynamics, and sometimes it will give non-physical artifacts. And to solve this problem is one of the important topic for SPH method research. So as we still have some time, I would like to introduce the open source code which my research group is developing. And this method is based on the SPH method, and the code is called SPHinXsys, which is basically means SPH method for industry and complex systems. So this open source code is so-called API. That means it's application program interface. It provides libraries and frameworks for SPH simulations. And with this library or API, you can write a SPH simulation code very easily. So this code is basically a C++ code, and if we use the API, the SPH API, SPHinXsys, to write a code, we can achieve fast and easy coding. For one example is we can do a 3D simulation with less than 200 lines of code. And this method is based on so-called multiphysics framework, which is designed for complex system and have a quite good extendability and flexibility. So this SPHinXsys code has three core components. One is called SPH body, which defined the interacting bodies. For example, one piece of solid or one bucket of a liquid. And the interaction between the SPH bodies was introduced by the SPH algorithm, which is, as we showed before, use SPH method to discretize the equation of motion to describe the physics between the SPH bodies. The third part is the code uses a third-party interface to combine SPH model with other model. For example, we combine the so-called multi-body or rigid body interactions together with our SPH code, and we can simulate quite complex physics system. So here is a typical application on flow structure interaction problem. So for example, in this case, we consider one channel with a wall, and in channel they have a flow, and within the flow we have an insert body, and this body have a two piece. One piece is a cylinder head, and then one have a tail. When the flow was flowing into the channel, and the solid body and the tail will be interact with the flow dynamic force. If the tail is elastic, so it's more like elastic beam, then the tail will be oscillated due to this vortex produced behind the cylinder. So this is a typical FSI interaction problems which we can use the SPHinXsys to simulate. Certainly we have other case, even more complex case we can simulate it. So for the code, we already published code in the public repository of GitHub. Then you basically can download the code if you want to have a try. Then we also have a document together go with GitHub code documents, and we just go together with the code. We have like 30 test cases with 2D and 3D problems, and if I think I will arrange one practice based on this code when one of my students will prepare the code, and we will put on the web, and you can have a try and have a practice. If you have interest, you can also write a report based on the simulation of this code as the exam materials.